Good afternoon. As you can see, my name is Eiman Kanjo. I am a professor. I work at two universities from UK. As you can see, I work in the area of Edge AI. Any of you has background in AI? A little bit here and there. Good. So I'll try not to dig deep into technical details, but over the years, I've been working on many projects that bring IoT, wireless technology, sensing technology, communications to solve real-world problems. I work in the area called pervasive computing. Pervasive computing is concerned about using the real world as our lab. So whether it's like a park or hospital or in the roads or, for example, for public safety, all of these are some of the challenges that we try to solve, and we work with end user organizations. So I've been working with IoT, wireless communication a lot over the years. And I also work with Edge AI Foundation. They are based in California, and Pete, the CEO, was here yesterday and he's here today, where we promote Edge AI systems and development, hardware, software. We have large presence and events and activities. So if you're interested, please sign to Edge AI Foundation newsletter and check out the website. I mentioned I've been working in IoT and wireless technology for a long time, but then over the years, the technology itself started to pick up, and the microchips started to be more advanced in a way that you don't just do communications like the IoT or the current or the previous IoT, but now you can run AI models on them, which is a great opportunity to process the data directly on the device rather than conveying the data, the raw data, to somewhere else, which could expose privacy and also, raw information about the user. So using Edge AI allows us to protect privacy. This is a screenshot of some of the current projects that we're working on with Japan on disaster management, where you could bring edge devices interacting with each others using low-power communications, and then you have AI model floating between them. So instead of just doing the AI on the device itself, but you also share the model between them. The way that we define TinyML Edge AI is like you have sensors, you have microcontroller or the device that can process, and then you have, of course, AI and machine learning. It has to be low cost, low power, real-time responses, and on-device learning and personalization. And most of the time when we do Edge AI development, we are concerned about optimization. We want to make sure that our solutions are optimized, accurate enough, low power, low latency, but this is hard. So sometimes we have to drop accuracy a little bit when we try to minimize the size of the model to fit in on a small device. So that's why we need to have this concept of Pareto optimal, where we try to balance all of these objective functions at the same time. And also there's the dilemma of like, how can you personalize or generalize? Like you could create a model that you personalize, you improve that model, but you could also share some of the parts of the model if needed. Like for example, the case of public health, where we share parts of our models in order for others to build larger models, or for doctors to access patients' data and build a global knowledge. But then it comes to some of the key concepts. So I mentioned Edge AI, which is like running AI on the device itself. And you already know centralized AI is like all the types of AI, like the language models that we use at the moment. But then also there's the concept of continuum learning, where you have Edge AI that has part of it continuing learning on the network towards the cloud. So it's not dependent on the cloud, but it utilizes part of the cloud to update and personalize the model. So this is one of the emerging techniques at the moment, especially in Europe. And when I talk about tiny devices, I mean, you've seen many of the devices. Seed Lab, for example, studio is here, and they have some of the smallest devices. So when I pick up a microcontroller, it should have wireless communication in somehow, or like energy harvesting, or some kind of low power tools. So it's not just the processor capabilities, but other capabilities as well. And they have to be small, like, for example, the case of drones or robots, we very often use a very tiny devices. So I'm more concerned about tiny ML rather than the bigger devices. So these can be put in, can be wearable, can be embedded wherever we go. And there are thousands and millions of them, if not billions. But what is interesting, so I don't know if any of you has a wearable device. If you have a wearable device, for example, let's say I could see that you're wearing some wearables. So one device has like 1, 2, 3, 4 megabytes, right? And maybe the other person has a few megabytes. And let's say we have 10 of these wearables. 10 multiplied by 4, you have 40. So 40 megabytes for a memory is a better equipped to run these AI models than one device by itself. And that helps us in a way that we could start thinking about resource sharing. Resource sharing means one device can't do too much, but if we share that model between these devices, share this memory, or even sensors capabilities between these devices, then we can do a better job. For example, in one place, as I mentioned before, in a disaster management case, or like wherever we want to apply it. We could share neurons, we could share weight of the model, and so on. So that's why I'm talking about the decentralized collaborative edge AI. This is like the next step beyond edge AI. In fact, this is the future of AI as we see it, the future of AI decentralized. So everybody's talking about these large models, OpenAI, LLM, and so on, where we say, instead of relying on these large models, why don't we do it locally, but still benefit from the connectivity between different devices. So this is beyond edge AI. This is the next generation of edge AI, if you like. And the benefit, of course, the data sharing, and the data sharing, the resource sharing, memory sharing, and so on. There's a concept collaborative learning. So you might have heard of distributed learning, where devices, this is an old concept, where distributed devices that can contribute to the computation. It's not just about AI. I mean, the distributed learning, distributed systems have been there for a long time, where people access computing power from different devices. But collaborative learning is very interesting, is that you have one device can do one thing, the other device can do another thing. Like one device can do, for example, vision, the other device can do audio recognition, the third device can do movement recognition. Collectively, these 3 devices, 4 devices, 10 devices can interact with each others. And what we end up with, more accurate model than the individual model. So let me give you an example. Imagine that someone is wandering around trying to find, or like 2, 3 people trying to find a missing person, right? If you have one person trying to find that missing person in the forest, he or she will find that person in like a few minutes or hour or something. If there are 2 people, you have 2 people trying to do this, will be better. 3 people will do it even at a faster speed. Same as collaborative learning. If you have multiple devices looking at it from different angles, so maybe one device is looking at it and the object is occluded 40%, where the other device look at it and it's occluded 60%. The other one is occluded 70%. Together, these devices can put a proper image of the missing person and find him or her faster. And that's why collaborative learning works. So devices have different weights in terms of their collaborative effort. And then there's the parallel processing, like what I'm talking about is really parallel. So you do things in parallel, you don't wait for one thing. So you could do parallel data capture, you could do parallel processing. There is a model that you could process in parallel, and there's a spatial. So in a way, like this region can process, and this region can process the model, and then you could merge them together. If you are interested in generative AI, this is a great deal because we work a lot on generative AI on the edge. And for example, here, if you have multiple devices interacting with each other, you could do multiple queries, so prompt splitting. Each device is querying the system, but from its point of view, and then together we have one unified query that it tries to solve a problem. And these systems can be heterogeneous. They can be one type of devices. So like in the missing person scenario, you could have cameras on all devices. But the disaster management scenario that I mentioned earlier, you have robot, you have drone, you have all sorts of things. And of course, that's why I'm here, because this is very relevant to low power, low energy, low cost devices. So these devices have to communicate with low power. Remember, they have very, very small memory. So very small memory and small capabilities and small processor. So they really can't handle a lot of communication. And then there's a concept of continual or incremental learning. So when you're doing this kind of development, just to show you here, so you have each device, right? So say this is one device that is running AI model. This is another device and another device. It has a local model and it has a global model. This global model gets updated from the other devices, and this one gets updated from the other devices. So they update each other's every time, and that's why we call it incremental continual learning, because you need to keep this process, or sometimes it's called adaptive learning, where they keep updating each other's, right? So the idea is that continual learning, that the model is never static. It has to update itself from the other nodes. So we call it incremental. But also, continual learning is a very interesting concept if you have, again, a wearable or you use it for health. So your model needs to be updated. So you get this wearable with a model that might be outdated after a few weeks. Your weight changes, your behavior changes, your symptoms changes, and so on. So it has to be updated by inputting new data. One of the issues with continual learning is that catastrophic forgetting. Catastrophic forgetting, for example, the model might forget the previous information and update itself with new information. Like when you do query on LLM or ChatGPT, sometimes you have a big set of queries and you taught the model to learn about this problem, but then it goes and follows the last prompt. Say, okay, how about the information I gave you before? It just forgot about it and just updates the model, the output based on the last input. So catastrophic forgetting is all about how can we make the model not forget the previous input, but at the same time, it's not dictated too much by the new input or not dictated too much by the previous input. So it takes, for example, the overall learning from many patients, but also from the current patient. I will skip this one, but we have been working in this area. I mean, if you're interested in this area, like how can we optimize and create a model that converges on all of these devices, whether it's like few or hundreds. And we have a paper if you are interested in this, if you follow my page. And you might have like a small cluster, you might have thousands, you have intra-clusters, you have inter-clusters, so all of them have to build like sub-models that can converge with the bigger models. We applied this in farming, in many areas, for example, and as I said, disaster management. I work with defense agencies, with city authorities, for example, pollution monitoring, with policing services. This is like a traffic interaction and networking. We have another paper in this area where you route the protocol and route the data and the model in a way that it is efficient. But there are many, many challenges. Some of these challenges, of course, how can you get a large test bed to run? So I have students, but it's very challenging sometimes to have like hundreds of devices and try to experiment with that. Having data sets is very hard. Imagine that you have a drone that's coming from a forest and going to a city, and the scene is changing, and you want to update the model. So having a data set that represents all of these scenes is really hard. So there are many, many challenges when it comes to these decentralized approaches, because you need to take into account the infrastructure, the test beds, which is something we're working on. And you have to make the system resilient, adaptable, and trusted. Just to mention a few things before I close, we have a new network on TinyML called TinyML UK, which will start in a few months' time. So if you're interested in TinyML and if you want to link with UK, we will start this network. We work closely with Edge AI Foundation, so we will try to run activities and link with Edge AI Foundation, but at the same time, our events and activities, we try to link with industry outside of UK, linking with the student, linking with academic, linking with all those interested in this area. And we have another funded initiative as well, where we also have some pots of money for small projects where we look at green spaces. So for example, we had many setups in the past where we use beacons, we use tags and other pervasive technologies to be able to connect people, to motivate them to walk faster and so on. So if you're interested in this, this is another funded activity. I'm happy to tell you more about it. And yeah, that's it. But the final message before I finish is that think about the decentralized AI. If someone tells you about what is the next thing in terms of AI, so I can tell you it's small and decentralized. There are cases where we still need the centralized approaches, but the centralized way is much cheaper, privacy protected, and it works towards democratizing AI for everyone. Thank you. I think we have no more time for questions, right? I mean, I'm around if you want.